just heard an interesting colloquium on brown dwarf by Kelle Cruz, and I hope she's here somewhere over there. Great. We also heard a very interesting colloquium yesterday by Scott Tremaine, who's visiting us from the Institute for Advanced Study. And speaking about that, the Institute is well known for being the stronghold of string theories. And then yesterday was April Fool's Day, and Scott is also from Canada, and the person that posted an April Fool's joke on AstroPH is Douglas Scott, and he posted this paper that is shown up there on string theory, which was very funny to read. I just wanted to read the last paragraph of that paper, which said that the string theory was called a bit of the 21st century physics that somehow dropped into the 20th century. Presumably, this was suggesting that string theory came to us from the future. But Douglas Scott thinks that a much more likely solution is that it came here, from another part of the multiverse. Perhaps then there are other universes out there in which string theory is not only simple and correct, but even falsifiable.
Thank you. I'll be sure to tell my colleagues that you reported on that.
According to Douglas Scott, he didn't get any response so far to this paper. Anyway, we have an interesting set of presentations today, as usual. We'll start with Xuening from the ITC, and he will talk about the Magneto-photoevaporation of protoplanetary disks. Then we'll move on to hear from Scott on warp accretion disks, Bardeen and Petterson versus Laplace. Then we'll hear from the colloquium speaker of today, Sarah Horst, sitting next to Karen. She's visiting us from Johns Hopkins, and she will talk about connecting scientists and teachers, planetary science in K-12 classrooms. Very important topic. And finally, we'll hear again from Kelle, and she will talk about astronomers and social media, how you can use AstroBetter, Facebook, and Twitter to be more productive scientist, educator, and mentor. Also a very important subject. Xuening.
Okay, thank you, Ali. I'm going to talk about something that is falsifiable. Although it's probably not easy to falsify because it involves magnetic field. So I have a long word in my title, but don't worry about that. I think all I mean is that I'm going to talk about how do protoplanetary disks lose mass? And this word, many of this word will become clear shortly. So this is the work I've been doing with a student, Jiani Ye from Shanghai Astronomical Observatory, and Jeremy Goodman from Princeton. So protoplanetary disks are where planets form. And many processes of planet formation will strongly depend on the global structure and evolution of these disks, which is determined by the processes of angular momentum transport and mass loss. A lot of my previous works have focused on angular momentum transport, and today I'm going to focus on the mass loss process. Conventionally, the mass loss process is understood as due to the so-called photoevaporation. The thermodynamics of protoplanetary disk is largely determined by the irradiation from the central star. And the bulk of the disk is very cold. While young stars are also produce a lot of high-energy radiation, from X-rays to UV. And this high-energy radiation, they cannot penetrate the whole disk, but they can strongly hit a very thin layer at the disk surface to several thousand degrees. And when the gas becomes sufficiently heated, they can overcome the gravitational potential well of the central star and escape. And this is basically a thermal wind, and it's called photoevaporation. And because this is purely a thermal wind, the mass loss rate will strongly depend on the thermodynamics. You have to get the heating and cooling right, which means you have to treat radiation and chemistry very accurately. And moreover, because purely a hydrodynamic process, the wind doesn't exert any torque to the disk. And so the mass loss has nothing to do with the accretion process. And existing photoevaporation wind models typically yield mass loss rate that is much smaller, a small fraction compared with the observed accretion rate for the bulk of the disk lifetime. While near the end of the disk lifetime, when the accretion rate drops, that's when photoevaporation picks up and can clear out the entire disk by evaporating, by blowing it away. So that's the basic picture of photoevaporation. However, there have been growing evidence that points to the importance of external magnetic flux threading these protoplanetary disks. There have been observational evidences, and also theoretically, if there were no such magnetic flux, there are basically no way to efficiently drive disk accretion to match the observed accretion rate. And when the disk is threaded by such magnetic flux, it seems inevitable that the disk will launch a magnetized disk wind from this classical magnetocentrifugal mechanism of Blandford and Payne. Basically, when there's external magnetic flux threading the disk as the disk rotates, the mass loaded to the field lines will be centrifugally accelerated. And this process will not only extract mass, but also extracts angular momentum from the disk, and so the disk will accrete. So at this point, it's really important to reconsider the problem of disk mass loss by in this new MHD wind framework, where the physics of the previous photoevaporation wind models should be incorporated into this framework by treating them as a thermal effect. All right. So while global disk wind simulations have existed for more than a decade, besides being increasingly complicated, when looking into the details, all these models, their parameter range doesn't seem to really fit to what the parameter range you would expect from the protoplanetary disks, and which I will cover in the next slide. And so at this point, it's, what we are going to do is, before we can perform a realistic global disk wind simulation of protoplanetary disks, it's very useful to construct a simple sort of a toy model that incorporates the essential wind physics. So the toy model we come up here is motivated from our earlier local disk simulations, which explains how the disk can launch the wind. But those local simulations, we can only see how the wind is launched. We cannot really follow the global kinematics. So that's why we come up with this global wind model. So the basic picture we have in mind is that the bulk of the disk is cold, and the gas is extremely poorly ionized, which means the gas and the magnetic fields are very weakly coupled. That's where you cannot really launch the wind. You can only launch the wind when the gas and the magnetic fields are well coupled. That happens in the very upper layer of the disk. So basically, this external high energy radiation, they not only strongly hit the disk surface, but they also substantially enhance the ionization fraction, so that at this upper layer, the gas becomes well coupled to the magnetic field, and that's where we can launch the wind. And from the standard MHD wind theory, so if you assume axis symmetry and steady state, then the property of the disk wind is fully determined if you know the poloidal field line geometry, and as well as the thermodynamics. And so that's what we do. We just prescribe the poloidal field line geometry to be a straight line with a constant inclination angle. Of course, this is a huge simplification. Nevertheless, by playing with this inclination angle, we hope to more or less cover the realistic situation. And the main physical parameters of this kind of toy model is that the main parameter is the poloidal field strength. Okay? And this can be constrained from the disk accretion rate. The typical accretion rate is about 10 to the minus 8 solenoids per year. And the stronger the magnetic field, the faster it can drive accretion. So there is a direct relation between the field strength and accretion rate. And for typical accretion rate, and you can translate it to somewhat more series-friendly unit, corresponding to the Alfvén speed as the wind launching point, to be about 0.1 times the Keplerian velocity or less. So this is really a weak field. While most previous global wind simulations, they are in the strong field regime. And another important parameter is the thermodynamics, which, for simplicity, we just treat the whole wind region as thermal with temperature of a few thousand Kelvin. And this translates to a sound speed of also about 0.1 times the Keplerian speed. And then we can explore these parameters. For our fiducial set of parameters, what we do is that we solve time-dependent MHD wind equations restricted to this field line. And we start from some arbitrary initial conditions. It doesn't matter. And then the system will just automatically relax to our desired wind solution. So what's shown here is the wind velocity as a function of radius. And you see the wind gets rapidly accelerated near the launching point and approaches some asymptotic velocity at large distance. And also shown here are the three MHD wave velocities. This is slow and Alfvén velocity and the fast magnetosonic velocity. And the point where they intersect defines the critical point. And here I want to particularly highlight this Alfvén point, where these two things intersect, and this defines an Alfvén radius, RA, and we see that this Alfvén radius is fairly close to the wind launching point. So RA is only about 1.5 R0. So what is the significance of this Alfvén point? Basically, it's closely related to how efficient the wind is transporting angular momentum. And there's a direct relation between this wind mass loss rate and the wind-driven accretion rate. And it's given by, roughly speaking, R0 squared, wind launching radius, divided by RA squared minus R0 squared. So if you plug in RA is 1.5 times R0, you come up with a number that is of order unity. This means this protoplanetary disk is likely losing mass fairly quickly. It loses as much mass as it accretes onto the star. All right, so this is that's the result from our fiducial parameter, which is presumably realistic, and we can explore the parameter further. So our main parameter is colloidal field strength. For example, before we explore the weak field regime, now we can increase the field strength, say, by a factor of 10 or 20, and which shown in this blue and red lines. And you can see in this case, the Alfvén radius becomes much larger. And therefore, if you plug into this formula, m dot wind over m dot accretion becomes much smaller, which makes this number somewhat more comfortable. However, if you increase magnetic field strength by a factor of 10, you get a reduced ejection to accretion ratio, but in the meantime, you also boost the accretion rate by actually more than a factor of 10. And now the accretion rate will become inconsistent with what you find from observations. So I would say in realistic systems, we are still in this weak field regime, and we expect strong mass loss. And another parameter is the thermal effect, right? We can explore the thermal effect by changing the temperature of the wind, which corresponds to different sound speeds. And we see that when we play with different sound speeds, I mean, this curve more or less overlap. And the only difference is that the location of the Alfvén point does change a little bit. So when you have a strongly heated system, sound speed is larger, and the Alfvén point moves somewhat inward, which means mass loss is somewhat stronger, which is consistent with your expectation. But nevertheless, this is sort of a weak effect. It's not a very sensitive effect. But it does affect the mass loss rate to some extent. So overall, I would coin this mass loss process from protoplanetary disk as Magneto-photoevaporation, which reflects both magnetic and thermal effects. And I put magneto in the front because I think it's more important. Right? So as a brief summary, just let's cross-compare the two scenarios. The pure photoevaporation scenario, pure hydrodynamic thermal wind, mass loss rate has nothing to do with accretion. While in this magnetized MHD disk wind, mass loss rate correlates with accretion rate. Accretion is driven by the mass loss. And for pure photoevaporation, it strongly depends on thermodynamics, while for this MHD wind, dependence on thermodynamics is only modest. Well, for pure photoevaporation, mass loss rate is typically much less than the accretion rate until the end of the disk lifetime. While in the latter case, mass loss rate is likely a significant fraction of the disk accretion rate. So there are obvious implications for global disk structure and evolution. For example, I would expect the inner part of the disk is likely to have relatively low surface density compared with standard disk models. But since this is a simple toy model, I don't want to speculate too much at this point. But another point that I feel really excited is that since this wind is launched from the disk surface several scale heights above the midplane, while most of the dust tends to settle to the midplane. So this wind is largely removing dust-free gas, and since the mass loss is so significant, it will likely enhance the total solid to gas mass ratio. And this will greatly promote several processes of planet formation, especially planetesimal formation, especially the leading theories for planetesimal formation require the solid to gas mass ratio to be enhanced by a factor of several above the solar abundance of 0.1%. And I think this is a promising way that you can achieve that to form planetesimals and to get the process of planet formation going. Okay, so that's all I want to say. Thank you very much. Right. Sorry, can you say the last sentence? Can you say the last sentence again? Yeah. Yes. 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 Right. 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 I think the most sensitive parameter is this, the Alfvén velocity as a wind launching point, whether it's comparable to the Keplerian velocity or it's much less than that. I think in the early phase of star formation, you have much higher accretion rate, and which means you have much stronger magnetic field. And so overall, the accretion rate is basically determined by how much magnetic field you have. And I would expect the overall process of star formation is a process that you gradually remove magnetic flux. At the early phase, you have more magnetic flux there. You have higher accretion rate. And in later phase, you gradually remove magnetic flux. You have smaller magnetic, less amount of magnetic flux, and you have smaller accretion rate. Whether this accretion to ejection ratio, I think observationally, is not a well-determined quantity. I think whether you have rapid, okay, this is not a well-determined quantity, but I would expect in the early phase, you probably have smaller m dot wind over m dot accretion. That's, while at later phase, as you remove a lot of magnetic flux, magnetic field becomes weaker, then mass loss becomes more significant at later phase. Yeah.
Yeah, I have a question about the non-magnetic field.
Right.
There you were saying that the accretion rate, was sort of independent of the wind, if I read that correctly. Mass loss
Yeah.
rate unrelated to the accretion rate.
Yeah.
But the amount of radiation that's hitting the disk, that's ionizing material and providing energy
Yeah.
for things to be driven. In some cases, wouldn't you expect there to be a direct relation between the mass loss from the disk and the accretion rate?
So that depends on what's the source of the high energy radiation, and it's unclear at this point, but very likely that the UV part of it is due to accretion heating, and so from this aspect, you also expect some sort of correlation. You accrete faster, you produce more high energy radiation, and then you can evaporate also faster. I think that's sort of what people would expect, but for the pure hydrodynamic case, right, that's the only energy source you can evaporate the disk. But for this magnetized disk wind, the energy of this wind is mostly powered from accretion. So you have additional energy source to power this wind. Yeah.
Okay. The purpose of this talk is to make a very simple physical point about warped accretion disks. This is work I've done with Shane Davis, who recently moved from CETA to University of Virginia. The subject of warped disks is interesting because there's a huge variety of warped accretion disks in astrophysics. On the small scale, Saturn's rings, debris disks around Beta Pictoris, quasars and microquasars, spiral galaxies, and X-ray binaries like Hercules X1, for which I don't have a suitable picture. The study of warped disks goes back to Laplace. He pointed out that around a planet with an obliquity relative to the ecliptic, the inner satellites orbit close to the equatorial plane of the planet, like the satellites of Mars. Outer satellites like the Moon orbit close to the plane of the planet's orbit, that is the ecliptic. And at each radius, there's a unique orientation for the satellite orbit at which the orbit average torque from the equatorial bulge of the planet cancels the orbit average torque due to the sun. And if you put all those orientations together, you get a warped surface called the Laplace surface. And if you have a dissipative gas disk, presumably how the satellites formed, with very small viscosity, it ought to follow the Laplace surface. Therefore, it's plausible that the satellite orbits themselves would follow the Laplace surface. In terms of the equations of motion, there's a simple equation for the torque with one component from the equatorial bulge of the planet with its J2, and the second component from the orbit average torque from the sun. And apart from rescaling, this is simple enough that the shape of the Laplace surface is determined uniquely by the obliquity of the planet. So when you solve these equations for the positions where the torque is 0, you get 4 solutions. This is the standard Laplace surface that's aligned with the planetary orbit at large radii and aligned with the planetary equator at small radii. I've assumed 60 degrees obliquity, so there's a 60-degree difference here. There are 2 pathological, unstable Laplace surfaces around the pole of the planet, and by the symmetry of the equations, there's a retrograde Laplace surface as well. In practice, you always focus on the standard Laplace surface, so there's one unique surface at all radii at which you expect the satellites to form. Disks got new attention, starting with a study by Bardeen and Petterson back in '75. They were interested in the case where you have an accretion disk around a rotating black hole. Because of the lens tearing torque, the black hole, the dominant effect of the black hole on the accretion disk at large radii is to give a torque given by this formula in terms of the spin and mass of the black hole. I would like to point out that this is not just a theoretical formula. Both because of Gravity Probe B and the Lagios satellites, we now have tests of the lens tearing effect to an accuracy of 20 or 30%. What Bardeen and Petterson pointed out, that if you assume that the black hole is misaligned with the large-scale midplane or symmetry plane of the system, the material will enter the accretion disk at large radii with a particular orientation, particular angular momentum vector. Since the black hole is tilted relative to that angular momentum vector with an angle you can also call the obliquity, the viscous stresses within the disk will cause the material to spiral inward along a gradually changing orientation until it ends up spiraling in along the symmetry axis of the black hole. Now, if you compare Laplace and Bardeen-Petterson, Laplace includes the central quadrupole and the companion torque. Bardeen and Petterson include the lens tearing torque and the viscosity. And you can see that although there are plenty of torques operating on a particular disk, there's no overlap between these two models. And so the natural thing to do is to ask what happens if you start to include more real other combinations of these torques. And the natural one to try first is the combination of the lens tearing torque and the torque from a companion, for example, the binary star companion that's feeding the X-ray binary. So just as a reminder, these are the solutions for the standard Laplace configuration. If you replace the central quadrupole torque with the lens tearing torque, you get a set of solutions that look like that. If you ignore the retrograde solution and the unstable solution, you can see that as the material spirals in, as you go along the surface, you reach a point where the surface disappears. And the only option the material has at this point is to jump discontinuously to a second solution, either this one or this one. So the conclusion is that if there's any obliquity anywhere from 0 to 90 degrees, and the viscosity is small enough, there simply is no continuous accretion disk around a spinning black hole. The equations of motion, in this case, are even simpler than in the case of the Laplace disk. This is what I gave you before. In the lens tearing disk, of course, the torque from the companion is the same, but you replace the quadrupole torque with the lens tearing torque. Interesting, at least for some of us, is that these equations are not completely original. They were originally given by Colombo, Bepi Colombo, who was a frequent visitor here many years ago. It was called Colombo's top and was a model for the orbital evolution of the spin axis of the moon. The reason for the difference in behavior is basically the difference in sign here. In the Laplace disk, if you have an intermediate orientation between the disk and the planet and sun spin axes, the torques are in opposite directions and can cancel. In the case of lens tearing, because of the change in sign, when you have an intermediate orientation, the two torques add rather than canceling. Okay, well, given this discontinuity is obviously unphysical once you have some viscosity in the disk, and so the natural next step is to look at what happens to a Laplace disk when you add viscosity, and to the Bardeen-Petterson disk when you add a companion. So we'll have three sources of torques in both cases. In this case, you have a one-parameter family of solutions. In the case of that Laplace looked at, the solution behaves more or less the way you'd expect. When the viscosity is low, you follow the original 200-year-old Laplace surface exactly, and as you add viscosity, the transition becomes more and more moderate. At high viscosity, the surface density of the disk is roughly a power law. At low viscosity, you get a sharper change in the behavior of the surface density of the disk close to the point of maximum curvature of the surface, simply because the additional curvature enhances the viscosity. And I should say we're using standard, complicated but standard equations from theory of warped accretion disks, most comprehensively given by Gordon Ogilvie in 1999. If instead of this you do the same calculations for lens tearing disks, what you find is when the viscosity is high, there's a smooth transition from the plane of the companion to the equator plane of the black hole. But as you decrease the viscosity, there comes a point, minimum viscosity, and beyond this viscosity, there is no steady state solution for the disk. And that point also corresponds to the point where the surface density and viscosity have to go to zero at a particular point, again, near the transition radius for the inviscid disk. Okay, so what do we conclude from this? First, that there are many sources of possible torques on warped disks. In addition to the ones I've discussed, there's also radiation pressure, the self-gravity of the disk, at least in the case of disks around active galactic nuclei, and so forth. Most calculations of disks so far have only looked at two of these sources. That's frequently too few. In particular, if you have a low viscosity disk that's warped by the lens tearing effect and a companion, there's an unphysical discontinuity at the warp radius. If you actually apply this to real systems, in particular X-ray binaries, quantitatively you find that the viscous torques are generally more important than the torques from the secondary outside of quiescence. So outside of quiescence, the Bardeen-Petterson effect is okay, but in quiescence, when the disk is relatively thin, the Bardeen-Petterson is not okay, and you have to worry about this discontinuous solution. If you look at AGN, what you find actually is that the dominant effects are neither of the above, neither the viscosity nor the torque from a companion, but rather the lens tearing torque and the self-gravity of the disk. That gives rise to a different set of behavior involving bending wave, the excitation of bending waves at the point of near the critical radius that propagate inward from the critical radius and again change the disk shape. Okay, I'll stop there. That's a reasonable question. The difficulty with doing good simulations with, say, of the MRI is that this is a situation that only happens with relatively low viscosities. That requires unusually high resolution in global disk simulations, which is quite hard to achieve. There has been an extensive program of simulations using SPH. Those have discovered somewhat different behavior, which I think is not related. They've discovered a behavior of breaking of the disk into two distinct orbital planes. I'm not quite sure what's going on there, whether it's an artifact of the SPH, whether it's a different physical effect, but I don't know. I'm just trying to tell you why I don't know the answer. The third problem is that the equations of motion due to Ogilvy are very sophisticated, but they're parabolic differential equations. What you really need is a set of differential equations that allow for wave propagation, set of hyperbolic equations, and that's still beyond the state of the art. My guess is that what happens is that you get some sort of boundary layer in which the viscosity is, as you say, enhanced, and as in the standard behavior of boundary layers, the layer is thin but has a greatly enhanced viscosity, and that permits the transition. But the basic answer is we don't know.
Scott, the Laplace problem, where there is no viscosity, no dissipation. So I'm trying to understand what is the solution, because if I tilted it from that solution, the orbit is not going to come back, right? It's going to precess.
Yes, that's correct. So
they are putting some dissipation? Or?
The Laplace solution should be thought of as a limiting case for the behavior in which the viscosity is non-zero but approaching zero.
Okay.
I have to give you the mic. Yeah.
In general. Sometimes, though, technology foils me. Okay, let's see if we can make this go somehow. So I just wanted to say thank you quickly, because I don't get an opportunity to talk about my outreach very often, which is actually very unfortunate. This is something that's very important to me, and I wish that I got to talk about it more often. So this project started out as the outreach component of my astronomy and astrophysics postdoc fellowship from the NSF. So just wanted to quickly acknowledge the NSF, as the funding for a lot of this came from them. So basically, how this project started was the Division for Planetary Sciences of AAS was looking to try to make our outreach a little bit more concrete. As the chair of the EPO committee likes to say, we're trying to get away from doing random acts of STEM, in which we kind of pop into a classroom, say, hi, what's up, here's a planet, and run away and never hear from them again. And so one of the things that we had heard from our membership was that they want to do more outreach. The scientists would like to do more outreach, and they don't know how. And so taking that into consideration, and also feeling like we want to try to maximize our members' time, we thought one of the ways that we could do that would be to interact with teachers. So rather than always sending scientists into classrooms, which I think is also very important, we can interact with the teachers, and that has a huge multiplier effect. For each teacher that we interact with, we're reaching all of the students they teach now and will teach in the future through this one interaction. And so the idea was floated, and what we decided to do was to run a series of teacher workshops that are concurrent with the annual meeting of the Division of Planetary Sciences. So one of the things that's great about this is that we have our entire membership together, which means we have a large collection of scientists in one place. And because our meetings move around, it means that we often will bring a large collection of planetary scientists to a place that doesn't have access to them normally. And so that means we can expose a group of teachers who have never met a planetary scientist before to a whole bunch of them all at once. And so logistically what happens is that we have a day-long workshop. We bring somewhere between 15 and 30 teachers to our venue. We spend the whole day with them. And throughout the day, we have scientists who are coming in and out, and we do a variety of different kinds of activities. But every year there's a theme. And so I just wanted to show you quickly the 3 different workshops that we've done so far. 2 of them were about Mars. The most recent one was about small worlds, because we are entering the year of the dwarf planet with New Horizons arriving at Pluto and Dawn at Ceres. And so we have a topic, And we have scientists come in and help the teachers get up to speed on the content knowledge. Because this is one of the challenges the teachers always tell us. I would love to teach about comets in my classroom. I don't know anything about comets. Okay, we can solve that problem. That's easy to solve. And then we also walk them through hands-on activities and things that they can use in their classrooms. One of the most important things about this, of course, is that we have to make sure we're tied to the state standards. And so that's one of the things that we spend a lot of time doing ahead of time, is making sure that if they are to do the things that we're helping them learn how to do, and their principal walks by, they have a piece of paper that they can point to and says, no, this is section C.3 whatever of the state standards. I'm doing what I'm supposed to be doing. Because I think any of you who've interacted with science teachers will tell you that they don't want to try to put anything more in their classroom. They're already struggling to cover what they need to cover. And so what we're really trying to do is help them use planetary science, right? Planetary science is kind of like an easy way to sneak your kids their vegetables, right? It's very interdisciplinary, but there's robots and volcanoes and planets, and kids think those things are cool. And also, it can be a good way in certain states where certain concepts in earth science are more controversial to be able to teach those. So if you're going to get in trouble for teaching climate change, you can teach Venus instead. Right? And you laugh, but it hasn't occurred to a lot of the people that make these kinds of laws that, in fact, Venus is an example of climate change, and so you don't get in trouble if you teach Venus. And so we're helping teachers figure out how to do that, to use the science to get their kids excited, but to also use it to teach the content that they need to teach. One of the aspects, though, that I think is really important, I don't have like tons of slides, but one of the aspects of these workshops that I found to be more valuable than I thought going into it is that we really try to bring our membership in as much as possible. And in doing that, although this slide is a really poor example, this is Dave Brain from the University of Colorado, I'm very, very cognizant of who I bring in to interact with my teachers. I want to make sure that I have a very diverse group of people, as diverse as I can pull from the membership. And one of the reasons for that is that many of our teachers have never met a scientist, which is kind of disconcerting when you have a high school science teacher, but it's true. A lot of them did not major in science in college, which is another problem. And so I really want to make sure that their idea of what a scientist looks like isn't limited to what they're seeing in the press. And I've had so many teachers come up to me and say, I've never met a female scientist before. And, you know, it just never occurred to me, and this is a horrible thing, but I've heard it from multiple teachers. It never occurred to me my female students might want to be scientists, right? So we're trying to also help change their vision of what a scientist looks like so that when they walk into their classroom, they see their students, all of their students, as people who might want to be scientists when they grow up. I think that's really important and something that we're able to do. One of the other things that we work really hard to do is to use real data. And this is something that, one aspect that I didn't point out, we have partnered very, very closely with EPO professionals who work for NASA. So I am not trying to reinvent the wheel. All of the activities that we use are validated. They're in all the various NASA databases for all the EPO and teaching activities, and we work directly with EPO professionals. So I'm not trying to be an EPO professional. That's not what I do. I connect our scientists and our teachers and our EPO professionals in the same room. And so we try to use real data. There's a lot of amazing validated products, not just for planetary science, but all of these things are true in all the other aspects of astronomy as well. And so there's a lot of things that are available. If you get asked to go into a classroom, you don't have to come up with something new. You can go and find these things. They exist. Someone who knew what they were doing made them for us. And a lot of people don't know that. One of the other things that we find is really important is going into a classroom and interacting with teachers. They know more about their classroom than you do. You know more about the science for sure, but they know more about their classroom. And so we spend a lot of time during the workshop talking about what are going to be the barriers to you implementing this in your classroom, and what can we do to solve that? Is it going to be a monetary barrier because your school district doesn't have enough money to buy the maps that you need to teach this lesson? What can we do to solve that problem? And another thing that we try very hard to do is to make sure that when we're going into an area that we're pulling from very diverse schools. So some of our workshops, the majority of our teachers come from schools that are in relatively poor areas where a lot of the students are on. One of the metrics is the lunch programs and things like that. And this is something that's also important to me, very important to me. And so we put a lot of effort into that as well. One of the other things that helps is to use STEAM instead of STEM. I don't know how many of you have heard this, but we're really trying to pull more art into some of these lessons. And there's this amazing, amazing program called Art and the Cosmic Connection in which, and you can just go download this and teach it to whoever you want if you want, but you use very simple shapes. Okay, what does it look like if there's a line on a planet? There's only a few options for lines on planets. There's only a few options for circles. But you can have the kids reproduce real planetary images, and in the process they learn about how these things formed. How do you know if something is on top of something else, right? How do you figure out the age of a stream, if it goes over something, if it looks like the crater was on top? These are all things you learn by drawing these images. And a lot of the teachers have told us that they have students who just doodle in their notes all the time, right? And these are kids who benefit a lot from having this kind of exercise and can learn science in this way. So this is something else that we've spent a lot of time working with. And one of the other things that's been really important too is, and this kind of goes back to what I was saying a second ago, there are tons of resources out there already, and we don't do a very good job of taking advantage of them. And so this is something that we're trying to work with our membership to understand, but also each teacher that we interact with, because a lot of them don't know that there are these big databases that exist where they can pull lesson plans from, because we haven't yet done a good job of integrating where NASA posts these things to the places that a lot of high school and elementary school teachers are pulling them from. That's getting better, but until then we can help facilitate that. I think one of the most important lessons I've learned from running these workshops, though, is that you should not be afraid to make a mess. So we have made giant messes in hotel rooms across the country from these workshops. So you can do impact cratering. We make stream tables, which are amazing. I don't know if you've ever done a stream table. The teachers, by the way, think these are awesome. You can see they're having a good time. And we make lots of messes. So if you're ever going to do something like this, you should probably make sure you have lots of wet wipes, because hotels don't like it when you do that. But we have yet to get, this is actually one of my proudest achievements, we have yet to get to lose our deposit. Although we may have come close a couple of times. So one of the other reasons that I wanted to tell you about this, though, is that one of the things that's great about each of these workshops that we do is that once we do it, we have kind of done it forever. And so we have all of the resources. We have a list of the cost breakdown for the materials. We have essentially a syllabus for the class that tells you how long each thing took, what order we did things in. This is all a lot of effort if you want to organize these workshops. But now we're pulling these resources together to give to our membership. If you yourself want to go and bring a bunch of teachers together, you don't have to do everything that we did. And going forward, we're going to make those resources available to all of our membership. And we're a relatively small part of AAS, but I would love to see other areas of AAS take this kind of thing on. And so if anybody is interested, please email me and I can talk to you about this. And one of the other things, I'm kind of transitioning off of the yearly part of this workshop, but we're getting ready to start building a network for our teachers. Basically, once you've done a workshop of ours, then you will always be part of this network, giving you access to all of the other materials, giving you access to all of our scientists if you want to have scientists coming into your classroom, and hopefully be able to kind of magnify the effect that we've had so far. But I would love to talk more about this if you want to find me later too. So thank you. So this is part of one of the really important things. Part of what I was saying about letting the teachers kind of teach is that that's one of the reasons we have kind of pause points throughout the day to stop and ask what the problems are, because we've run into all kinds of things I never would have imagined. There's this amazing activity called edible planets, where you build these layered things out of like Rice Krispie treats and all this stuff, and 3/4 of our teachers were like, "Oh, this is amazing. We're going to do this in the classroom." And one of the teachers was like, "Do you know how many allergens are in these things? Like, I cannot bring this into my classroom." And so we stopped and we sat and we brainstormed. Okay, how could we do this without these materials? And it's going to be the same kind of issue. We haven't had religion come up yet, but that would be the same type of thing where if that was something, then we could stop and talk about it. And it's really important. I don't want them to come and spend the day with us and never use any of this again. And that's part of the reason that we try to make sure that if something is not going to work for them, while we're all in the room together, the scientists, the EPO professionals, and the teachers in that moment, we can brainstorm how to solve the problem. And I think that's been really effective so far.
So how do you evaluate the impact that this workshop has? It sounds like you had a lot of fun, the teachers had a lot of fun.
So we do all kinds of metrics. So we do pre and post exams, basically, of content knowledge. We also do a survey about how they felt the workshop went and improvements and all of these things. And then we're doing follow-up surveys, a year on or something like that to see at least how their content knowledge is going. One thing that we haven't been able to do yet, and it's part of what I'm working towards in terms of trying to build this up a little bit more, is to have more follow-up contact with the teachers. That has turned out by far to be the biggest challenge of this whole process. Because part of my intention at the beginning had been to try to maintain as much contact as possible with the teachers afterwards. And I'm busy too, but they're so busy that I get no response. All three of those workshops were actually tied to missions. So the first one was tied to Mars Curiosity, the second one was tied to Maven, and then the last one was tied both to New Horizons and Dawn. And so, Curiosity landed on Mars, and I sent out, an email to the teachers and oh my gosh, there's this and there's that. And I have a list of people that would love to Skype with your class and they can answer questions about the Mars rover. And I got exactly 0 responses from my teachers. And that's been the challenge this whole time. And so that's something that is going forward, really the main area that I want to focus on from now on. And so we haven't been able to do that as much as I would like, unfortunately. It's a combination, and you may have noticed, let's see, places where we have existing networks, it's much easier for us to find teachers. So in Tucson, we had 15 teachers, in Reno, we had 10 teachers, and in Denver, we had 35 teachers. And the reason for that is that one of actually the big STEM companies, McCrell, which some of you may have heard of, is based in Denver. And they just have this extensive listserv, basically, of all the different school districts in the whole area. And so that's how we start, is basically, okay, who has one of these lists? So we email principals. We'll start sending out emails for the next one this next month. So we send a save the date the previous school year, just so that they know we're coming. And then in the fall, we just start emailing people. And so this has been one of the things that has been probably the most work for me leading up to it, is trying to make sure that we don't only end up with private school teachers, or we don't only end up with high school physics teachers or something. We've had a great diversity of teachers, which has been really amazing. And one thing that we have done, and this is something important to think about if you do have any interest in this, is that we tried really hard for a while to be able to offer them continuing education credit, which is another thing that turns out to be somewhat of a nightmare to organize. But it's totally possible if you know who to talk to. But so far, every school district that we have had any interactions with, even them just having a piece of paper that we printed out for them that says they spent 8 hours with us, actually helps them. And so that's another way that you can incentivize having the teachers come. The workshop is free for them, which is really important to me. We provide a lovely breakfast and lunch and try to make it a really nice experience and show them that we value them and that we think what we're doing is important. And so we haven't had a horrible time getting teachers for the most part, but it does require a lot of legwork. But they're all super excited. I mean, they show up at 8 o'clock in the morning, and they spend 8 hours with us. I can't even move or talk by the end of this workshop, and they're still like, planets are amazing. I'm like, yeah, I mean, sure, I guess, why not? And this one's okay, but so it's been a really good experience so far. But yeah, that's another one of the challenges. Oh yeah. Absolutely. I had to teach for 3 solid hours last week, and I almost died. And then I was like, God, K-12 teachers do this all day, every day. I don't know how that works. Thanks. Almost ran away. Let's see, which thing first? Plug it in while there you go. I'm still stuck.
Yeah, and I don't have a pocket either.
Oh.
Does it have the thingy on it?
Yeah. feel like you try to use those things and then they like snap. It won't help. Yeah. Here. This is what nice to have you up here.
Yes, it is.
Good.
Yeah, I think so. Is that good? Can you hear me? Good enough? Maybe? Good enough? Well, you're right there. It's easy for you. No, I think I hear a little bit of an echo. That sounds good. So I do need internet. Guest access. Excellent. Success. Close. So hi, my name is Kelle Cruz. Also, thank you for the opportunity to give the second talk. Usually when I go someplace to give a science seminar or colloquium, I actually ask specifically to give a professional development seminar or something like that. And so it's really nice to have this already set up. The theme of what I want to talk to you in my 15 minutes is using this thing called the internet, which I think most of you have heard of, to foster collaboration and information sharing amongst scientists. And it's something which we really value, right? We really value inviting people to come to seminars. We really value going to conferences and interacting with our colleagues. We really value emailing within our collaboration. We really value reading other people's papers. But it turns out that the time scale on which we can have those interactions is so much faster now, and we can really broaden our access to who we get to talk to, what we get to talk about, what kind of experts we get to talk to. I also, I don't think I have been in a room with this many astronomers in a really long time, that you get this every day. You're in such a privileged position. And for a lot of people who are at smaller institutions, just don't have access to a bunch of expertise to be able to walk down the hallway. And so the internet is really allowing us to both, for the professional astronomers to have access to the other people who are already at our level, who normally we only get to interact with at our specialized conferences, but also for people who are at smaller institutions to have access to a really wide range of expertise and knowledge. So I want to talk about a couple resources. The first one is AstroBetter, which I feel like at this point everybody's heard of AstroBetter, right? Yes? Make me feel good and say yes. Yes. Good. So AstroBetter is a blog and wiki for professional astronomers. It is not about science. It is about doing science. It is about all the things which we don't get taught in classes, right? It's about teaching, which we don't get taught to do. It's about good communication, which we don't get taught to do. It's about good programming, which we don't get taught to do, right? It's about all the things which are extremely networking and job hunting and giving good interviews, right? All the things which are crucial to being a successful scientist, grant writing, right? Which we aren't taught to do, and so that is the content of AstroBetter. And so I just want to, it is a blog which is quickly becoming an outdated mechanism, but we'll figure out how to solve that problem later. Actually, I need to do Apple minus, I think. Not that one, the other one. Everything's going bigger. View, zoom. How about reset? Okay, that's the same as it was before. So the most recent post on AstroBetter is actually about printing your posters on fabric instead of printing posters on paper. And so it's a pretty extensive, this is the kind of fabric to use, this is what it looks like. There's comments in the bottom, so there's 8 comments on it, which someone was like, oh, I use this other kind of fabric, but I need to iron it after. And it's also super cheap, and about the timing issue. All of these things, right? So this is the kinds of resources around AstroBetter. Before that, I wrote a post. I also use AstroBetter as a medium of a little bit of an opinion page, right? It's not an official thing of anything, so we can express opinions, right? It's not in the AAS newsletter. Kevin Marvel didn't sign off on this because that would have been impossible. Talking about how, especially for the more junior scientists, when there are political things going on that impact the whole field, it's like, what's the backstory behind this? How is this going to impact us? What does this mean? What are all these acronyms? I think a lot of the discussion on AstroBetter was really important around the decadal review. When the decadal review, when New World Horizons was happening, when the town halls were happening, a lot of, all the way from first postdocs, junior to that, don't know what all these missions are, don't have a sense of how to have a 10-year plan and what happened in the last one. AstroBetter provides a way to give that kind of information. So the last thing I want to say about the blog part is that I absolutely consider the blog, and I can't adjust the sizes. I've got to be able to, come on, view, zoom, zoom out. View, zoom out again. View, zoom out again. So I just want to show the number of posts by contributors over here on the side. And this strange person named Guest is starting to catch up with me in the number of posts. And so now that I have a tenure track faculty position, and I'm I did a lot of the posts actually when I was a postdoc, but I'm posting much less. And AstroBetter is really becoming a forum for everyone else to share their awesome things. Sarah, we need an AstroBetter post on all of these resources, right? It's a yeah, you contribute to the wiki, but the blog post can be a really useful announcement of this is what things are doing. This is a resource which is not really well known, and it also is discoverable, more easily discoverable as well. So I absolutely I consider AstroBetter to be a community resource. If there is something which you think like, oh wow, like I really kind of want to write like a one-page Astro PH on this, or maybe I should just put this on a web page, or how this is something really neat which I think other people would use. How do I communicate that to other people? Please send me an email, kellecruz@gmail.com. Send me an email and say, hey, there's something which I'm thinking about which might be a useful guest post for AstroBetter, and I'll work with you. I'm an editor. Now I call myself the founder and editor of AstroBetter. I'm not so much a blogger anymore as much as I am the editor of the site. We're also Sloan funded, so Sloan is very happy with the impact that AstroBetter has had on the field. It's been very impressed with us and wants to support it. And so I even have a content manager who helps with the editorial process, who will help you do the links and help you find images and give feedback. So please consider AstroBetter as a community resource. If you want to use it to promote your own thing, please do. It's not mine, it's ours. So that's one component, the blog, which is a little bit like you can think of this spacing is all cattywampus. Awesome, there we go. I see, that's just what I needed to do before. So in addition to the blog, which is essentially like a newspaper, which it's one post, which is informational, and you can comment on it, but you can't change it. One of the really fast-growing resources is the wiki. And so y'all know what a wiki is, right? You sign up for an account, and then you can edit the pages. The only page, so the rumor mill is hosted on the AstroBetter wiki. The reason why I tolerate hosting the rumor mill on the AstroBetter wiki is because it forces people to create an account so that when later you want to edit other wiki pages, you already have an account. I'm tricky like that. Right? And so I'm lowering the barrier to entry and the discovery potential of the scientific and tool resource content on the wiki by hosting the rumor mill. And the rumor mill is the only page which you can edit anonymously. All the other pages do require you to log in order to edit. There are some really, really useful wiki pages on here. There's a setup guide for Macs, for astronomers, that has like the latest links to how to do the Python install, how to do the IDL install, all of those things. There's I think one of the underused pages, which I think, was it Sarah that you discovered the refereeing one? So other resources, refereeing and peer review. So just a couple years ago, someone was like, man, everybody does refereeing and peer review differently. And everybody learns it from their advisor. It's like, what are the things that we agree upon about what are the standards for referee and peer review? And so we wrote a little guide there for refereeing and peer review. I put my ideas for best practices for keeping lab notebooks. And so this is a resource, which is a community resource, especially I think for most of the people in this room, maybe not necessarily for you, but for your students. Right? You don't necessarily need to use all of these things, but you can point your students to say, I'm sure there's something on AstroBetter about that. Get out of my office. Right? Go find it. It exists there. And then if there's anything which you want to change or you want to update, it's a wiki. Please change it. Please update it. Don't send me an email to change something on the wiki. Just change it. Right? Just fix it. If you want to add something, just add it. Okay, so there's the wiki. Facebook. I also want to talk about Facebook. So I know lots of people have a negative visceral reaction to Facebook, and I get it. However, it is an extremely powerful platform for enabling us to communicate with each other about our science on a daily basis. Right? I don't read AstroPH anymore because we have the low mass stars and brown dwarfs Facebook group where all of the experts in my field post their papers, and then all the experts discuss them just like if we were at a topical brown dwarf conference over beers. Right? It is access to that kind of information really fast. Wow, that went by really fast. Summary of if your subfield doesn't have a Facebook group, so there are many, Compact Binaries has a Facebook group, Direct Imaging of Exoplanets has a Facebook group. I highly, highly recommend, if your subfield doesn't have a Facebook group, to consider making one. It has really changed the dialogue and the advancement of our field and the way we comment on each other's papers and comment on each other's science. My students, my undergraduates and graduate students, are not required to post to this Facebook group, but they are required to read it. Right? This is the current events of science in our fields with the experts, really weighing in on an everyday basis. I just have to talk about Twitter. Okay, one more minute on Twitter. And I'm also going like an advanced level of social media, right? If you do one thing, just the blog, then the wiki, then Facebook, and then Twitter. Twitter is also an extremely useful resource for bringing us together, right? There are so many people in this room, so many people, like 5 people, Sarah, John, Ruth, Alyssa Goodman, who's not here, who I communicate with all the time because we're on Twitter together. And it really brings the community closer. So this is someone just posted this yesterday, been tinkering with, right, there's no long slit spectra data reduction thing in Python, and that's just terrible. Let's move together on this. And so here's a discussion with all of the Python and spectra gurus basically just in the US for right now, about the process, who's all doing this and what resources to keep. And that was just like an hour conversation, right? So Twitter is also really useful. I want to make my final comment about diversity mentoring and what astronomy looks like and the usefulness of Twitter. I have noticed anecdotally that women seem to be very comfortable on Twitter. And that if you look, one of the most useful things that Twitter is for back channels at conferences. And so there's been some studies recently that show women are more hesitant to ask questions. They're more hesitant to raise their hand in a big thing. But if you look at the back channel at conferences on Twitter, it's dominated. We're very overrepresented on Twitter. And so I think that, I don't know what's going on there, but I do know that there's a strong co-mentoring network of women on Twitter, and there's a lot of diverse voices on Twitter. And so not only do I think that's really important for everyone to have access to that diverse set of voices, it's also important that it's a place where we find that community that we may not otherwise have at our own institution or in our own subfield. It's a really great network of people, which I encourage you to encourage your students to at least consider. That's all. Thank you. Comments? Apprehensions and fears? Peter? Yeah, someone must be. Someone.
Almost certainly, someone was.
Almost, I don't know.
Tweeting my talk. Thank you wherever you are.
Peter. Do I want to thank you for that leading question? So what Peter asked is, do I want to say anything about science better? I guess I have to now. So I've started a consulting company. It's called Science Better Consulting. It is in its very early stages, but the vision is to be able to connect people with individual skills with projects that need those skills. So for example, let's say you have a data set and you want to use MCMC to model your uncertainties. You could get a graduate student who's going to take a long time to learn all the code to figure out how to do that. Or maybe you could spend, let's just say $500, $1,000 of consulting money to bring someone in who's an expert who really knows how to do that and can probably do it for you pretty quickly. Let's say 2 days, right? And doesn't even need to travel to do it, right? You can do it remotely. So ScienceBetter Consulting is an infrastructure thing, a piece of infrastructure for the astronomical community to connect projects in need of specific expertise with people in the field who have that specific expertise, who can do things quickly. We could also use it, for example, for making your group web page, right? Even something as easy as that, which the web designers don't do it right. They don't know what science web pages should look like, but there are probably some grad students who, instead of tutoring on the side, could be making web pages for everyone. Also outreach. So for example, let's say as part of one of your broader impacts for your NSF proposal, you'd like to implement some of Sarah's thing. Sarah would like to help you with that, but Sarah deserves compensation for helping you implement that outreach project in a different place, right? So ScienceBetter Consulting would provide the infrastructure. I would hire Sarah as an independent consultant. Your institution hires ScienceBetter Consulting as the consulting agency. Sarah gets paid $1,000 to come help you with your thing, right? Thank you, Peter.
There is another question. Usually among young people it's thought that communication is just an official, but there are no negatives to it. But there are actually negatives because, well, one of them is that when you speak to a person, you see the person typing in front of you, which is not necessarily very polite way to have a conversation. But the other one is that people do not think independently, that they are constantly bombarded by communication from other people that maintains sort of a common way of thinking of things. You don't find that
No, I find that my views and understandings are constantly challenged and broadened by being exposed to a larger voices, right? So something that I would absolutely like post to the Low Mass Stars and Facebook group, or even to Twitter, which is that I'm thinking about doing this way. Do you think that's a good idea? Or I just got this big data set. I was going to reduce it using this. Do you think that's a good idea? You know, how would you do it? And then you get a whole bunch of opinions about how you would do it. It's.
Do you have a day where you can completely disconnect yourself from the world independently of the problem? Or
Of course.
Eager to check what?
Well, okay. So those are two different issues, right? We have a societal problem with all of this, with the addiction to the phone. I absolutely agree. That's an issue. That is not enough of a problem to discard the huge benefits that we get from having right science. We are going to be able to do our science better and faster because we can communicate with each other more often, right? Because I get access to not only my favorite collaborators are going to comment on my paper publicly on Facebook, but also the biggest critics are also in my Facebook group, right? And so it's not going to just be like, oh, someone asked a really biting question at a conference that we have once every 2 years, right? That conversation gets to happen often in real time. And that's better for science, right? That's better. That's better. And I think on an individual basis, yes, you have to struggle with Twitter. I don't have my Twitter on all the time. I don't log into Facebook all the time. But there are some questions where my students ask me, it's like, I don't know the answer to that. You should ask Twitter. And we get great, we should post that to the Facebook group. And we get a lot of really great responses. And we also build collaborations and we find people that we would not otherwise be collaborating with. So pros outweigh the cons is the answer to your question. Yeah.
That's it for lunch.
Yeah. Thank you.